Tonight on Nova, the Northern California earthquake of 1989 was the most expensive natural disaster in United States history. It was also expected. The effort to predict earthquakes spans centuries. The story is a roller coaster ride filled with stunning revelations and catastrophic failures. It ends with new insight into when we can expect the next earthquake.
Funding for NOVA is provided by Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. And the Johnson & Johnson family of companies, supplying healthcare products worldwide. Major funding for NOVA is provided by the financial support of viewers like you.
October 17th, 1989. Santa Cruz, California. It's an easygoing town nestled beneath the mountains of the Northern California coast. A visitor once called it an outpost of Eden. But the San Andreas Fault curves through these mountains, pushing them up with earthquakes. Another is due, according to scientists. In a new kind of forecast, they offer probabilities as high as 85% over the next 30 years. On this day, underneath a mountain called Loma Prieta, probability became reality.
Leadership. It's a co-opting, it's much more similar to the Mexican free idea.
At 5:04 p.m., Latin American Studies 1 was underway at UC Santa Cruz.
And they have a candidate who's very strong and is fighting with us for second place.
With video cameras everywhere, this was the most visible earthquake ever.
So the Oakland A's take. Hey,
what, we're having an earthquake.
In downtown Santa Cruz, the shaking was over in 20 seconds.
And all of a sudden it started to shake a little bit, and then it started to warm.
Please get off the avenue. You can't expect further aftershocks. There will be more building collapse.
Most of the old masonry buildings were beyond repair. A plan to reinforce them had never been agreed upon. People were injured. Some were missing. Volunteers put themselves at risk from aftershocks. With power out and telephones overloaded, the town was on its own. Like most of San Francisco, Candlestick Park withstood the impact. The stadium was built on bedrock, it had recently been reinforced.
Ladies and gentlemen, power has been interrupted. The game has been called. Can you please leave the stadium in an orderly manner?
Other structures fared less well. The Bay Bridge was built to withstand such an event. But that was in the 30s, before much was known about earthquake engineering. One stranded driver made a video record.
This is the crack down there. They sent us down here, surprisingly, in the wrong direction. There's another car. Gosh! Thomas, we need to go down there and help.
Heading south onto the Nimitz. That is completely collapsed.
The worst disaster lay across the bay in Oakland. A section of road atop the two-level Nimitz freeway collapsed, crushing 53 cars below.
No, he's alive. He's trapped in there.
No, you're in your truck.
And he heard me and then he parked outside.
Your truck is upside down.
Man, this is over.
Need something to pry the door. And he's getting to pry the door open.
Screaming and just begging us to get him out. We tried everything.
The freeway was built in the 1950s, before concrete structures were designed to be flexible. The road was slated for reinforcement.
There's a gas leak. Let's go. Turn around and go that way.
In the Marina District, the soft landfill caused houses to topple and gas and water mains to break. A lethal combination.
Right now we have a major fire burning in San Francisco's Marina District. A building there collapsed and burst into flames as another building across the way from it on the northeast corner of the...
As emergency services worked through the night, scientists at the United States Geological Survey began to assess what had happened deep down in the earth. The unspoken question: was this the earthquake that had been forecast?
Pretty quickly we knew where the earthquake was, and as soon as we knew where the epicenter was, honest, we all knew what had happened. We all knew it had been precisely that segment we had been concerned about, and that long-term forecast had been fulfilled.
The apparent success of the forecast was affirmation for a new approach to earthquake alerts. Long-term forecasting is an attempt to give communities years or decades to prepare. But scientists also continue to search for the means to predict earthquakes, so they can issue short-term warnings in the days or hours before an event.
We came closer to predicting this earthquake than we've ever come before. However, that's much less than half a loaf. Our job is to predict earthquakes and save lives, and clearly we didn't predict it in any sense that could have saved any of the people that were killed in the collapse of buildings or freeways.
Short-term prediction remains an unfulfilled goal of earthquake studies, so scientists are on the lookout for some kind of warning event. They call them precursors. For example, small earthquakes are common before a large one. But these foreshocks are hard to recognize, and this time there had been none. But something else had preceded this earthquake. Near a town called Corralitos, only 3 miles from the epicenter, an experiment was underway that had nothing whatsoever to do with earthquakes. An antenna had been installed to monitor naturally occurring radio waves, part of a communication study for the Navy. Anthony Fraser Smith, a Stanford physicist, found that unusual low-frequency radio waves had preceded the earthquake. He wondered whether the squeezing of the earth before the fault ruptured had produced them.
3 hours before the earthquake, the activity went up to a level where you don't normally see it at all. And then the earthquake struck, and then we lost electric power, and we didn't have any more measurements. We've been recording at this Corralitos site for 2 years. We haven't seen anything like these big signals coming through.
If Fraser Smith's observations could be repeated, perhaps next time there would be a warning. But he faced a paradox all too familiar to earthquake scientists. In order to repeat his experiment, he would need to locate his antenna near the site of another earthquake. He would have to predict an earthquake to test his experiment in earthquake prediction. Often, earthquakes leave physical evidence, but even so, they remain elusive. To recognize patterns, geologists need to compare dozens of events. Yet few here now will be alive when the next earthquake takes place here. Earthquakes remain the most difficult of all natural phenomena to understand, much less predict. The recent achievements in forecasting are the result of efforts that have been ongoing for over 2 centuries, all inevitably pushed ahead by the devastation of another earthquake. The first important understanding of these events followed one of the greatest cataclysms of recorded history. Lisbon was one of the richest of European capitals, and during this time of Inquisition, earthquakes were an indication of divine wrath. On All Saints' Day of 1755, most of the 250,000 residents were in church. The city began to shake. Terrified worshippers rushed outside, calling to God for protection. Then came a second, more powerful shock. The ornate facades of all the great buildings collapsed, crushing the crowd below. Those that survived faced a tidal wave. Then a fire that burned on for 3 days. 60,000 people lost their lives. Lisbon's great medieval buildings and masterworks of art were incinerated. But there was something to be learned here. A review of first-hand accounts revealed that the earthquake had produced 2 distinct types of motion, a tremulous vibration followed by a wave-like undulation. The understanding of these vibrations would be advanced by the development of the seismograph. It was an instrument that could record and display these seismic waves. The Milne Gray invention of 1885 was the first practical machine, and in principle was simplicity itself. A heavy pendulum remains stationary because of its inertia, even as the world all around it shakes. The seismograph was able to record 2 distinct types of waves. A primary, or P wave, arrived first. This was followed by a secondary, or S wave. The faster P waves moved through the earth like sound waves, compressing ahead, expanding behind. S waves are slower because of a lateral shearing component which is particularly damaging to buildings. Because the waves travel at different speeds, it was possible to compare their time of arrival, then compute the distance to an earthquake. By the early part of this century, seismographs were linked in a global network. With data from 3 observatories, an earthquake anywhere in the world could be pinpointed through triangulation. The first seismographic stations in the Western Hemisphere were at UC Berkeley, and for good reason. The San Francisco area had suffered 2 quakes since the gold rush, but these seemed trivial alongside 6 major fires. Nonetheless, the region was booming. The demand for land was so great that sand dunes, along with almost anything else, were shoveled into the bay to create fill. It was already clear that this kind of land did not stand up well to earthquakes. But the practice continued, and the city grew. In 1875, doors opened on the Palace, the largest hotel in the world. It was built to be earthquake-proof and had its own water supply to fight fires. During the spring of 1906, Enrico Caruso, the world's greatest tenor, came to sing. He stayed at the Palace. On the morning following his performance, the hotel guest experienced a tremor, then a stronger one. Caruso was thrown out of bed. Everything in the room was going round and round, he reported. The chandelier was trying to touch the ceiling, and the chairs were all chasing each other. My God, I thought it would never stop. It lasted for almost a minute. The palace survived, but not less well-built structures on fill. Caruso was next seen with his trunks, dressed in pajamas and a fur coat. Hell of a place, he muttered. I never come back here. Water mains had broken, and it was impossible to fight the fires that started to sweep the city. As the days passed, there was increasing chaos. When the blaze finally approached the palace, firefighters tapped the hotel's cistern. Water supplies were exhausted and the flames swept through. After 3 days, the fire stopped, out of fuel. Nearly 3,000 people had died. It was history's greatest conflagration. Interestingly, the man who probably knew more about earthquakes than anyone was photographing damage across the bay in Berkeley, unable to reach San Francisco. He was the great American geologist Grove Carl Gilbert. Gilbert participated in the epic scientific study that followed the San Francisco earthquake. He took photographs, sometimes using his wife for scale, and described much of what had taken place along the 290-mile rupture. Gilbert was well ahead of his time in understanding the behavior of the San Andreas Fault during the earthquake. He describes a fault as a crack in the Earth's crust caused by strain from movement deep below. Each side of the fault is held tightly in place by friction until enough energy is built up to overcome it. The release is so swift that it creates seismic waves. This is followed by decades of quiet, during which the strain builds up again. Gilbert wanted to study the possibility of forecasting a recurrence of the San Francisco earthquake. Decades would pass before that idea was pursued. In 1915, San Francisco was proud host to the Panama Pacific International Exposition. As much as anything, it was a celebration of the city's rebirth. The lavish fairgrounds and pavilions were built on landfill. After the exposition closed, the land was subdivided for residential housing. The new district was called the Marina. The first half of the 20th century saw the development of more sensitive and accurate seismographs to record earthquakes. The Vickert recorder was state-of-the-art when it went in at Berkeley in 1910. Seismograms remain the basic record of an earthquake. From their tracings, a seismologist can calculate not only location, but also the direction of slip and the energy released. Sometimes even the length of the rupture. The amplitude of the largest wave is measured to determine the magnitude of the earthquake on the scale developed by Charles Richter. Because the range of energy release is vast, the scale is logarithmic. The difference between a magnitude 6 and 7 is 10 times. Between 6 and 8, 100 times. Although Charles Richter was not a conventional man, as he proved as a practicing nudist, he kept the door closed on earthquake prediction. He liked to say that only fools, charlatans, and liars predict earthquakes. It would take a revolutionary new understanding of the forces driving earthquakes to bring prediction closer to reality. In the 1960s, it was proposed that sections of the Earth's crust, outlined by earthquakes, were actually moving. According to this theory, great underwater ridges are pulling apart. The ridges move out like a conveyor belt. New ocean floor is formed by magma swelling up from the hot interior, like this lava off the coast of Hawaii. When the ocean floor moves into a landmass, it is forced down under the continental crust, producing earthquakes and volcanoes as it goes. The gigantic ocean trenches, like those off Alaska and Japan, are the location for this subduction. In other cases, like India and Asia, two continents collide. There is no way to go but up. The Himalayas. Along plate boundaries like the west coast of California, sections of the crust grind past one another, sticking, then breaking in earthquakes, creating the San Andreas Fault. The theory of plate tectonics, as it came to be known, was one of the great discoveries of the 20th century.
I don't expect in my lifetime to see something in the earth sciences that is so all-encompassing as this. It really provided, for the first time, a picture of the earth and how the earth's surface is moving, that provided an explanation for why most earthquakes occur where they do.
The theory was put to the test in the new state of Alaska. In 1964, Anchorage was a boom town.
Revolution Airways, Flight 3.
With an international airport, it attracted commerce and tourism from around the world, while rail links brought in freight overland from ocean ports. March 27th was Good Friday. and at Valdez Harbor, the cargo ship China was unloading the first fresh fruit and vegetables seen here in months. On deck, a sailor shot home movies, unaware he was about to record one of the greatest earthquakes in history. There was a terrible lurch, and the harbor started to empty. A chasm opened directly alongside the ship, and the China began to sink. The entire landmass around the dock softened and collapsed into the sea. In Anchorage, the shaking lasted 4 minutes. At Seward, gas tanks and pipelines ruptured, spewing out their blazing contents. The displacement of the seafloor created a series of giant waves called a tsunami. It slammed coastal communities as far away as California. A survey of the earthquake's effects began the next morning. Progress was impeded by the devastation. One geologist, determined to make his way in, was George Plafker.
Well, the first thing was that we couldn't land at the Anchorage airport because the international airport tower had collapsed. It was pretty shocking, especially if you've never seen anything like it before. Individual homes were moved a quarter of a mile, 1,400 some feet, laterally on these large slabs.
The slabs had traveled on loose layers of earth, which had been liquefied by the tremor. The quake hit with a magnitude of 9.2, yet surprisingly, only 114 people died. Alaska's population was small, and schools and office buildings had been closed for the holiday.
By then, we had word from the civil defense and the military that there were waves that had just demolished towns, and that there were other strange things that had happened, like land level changes. Apparently, the tides either went out and didn't come back, or they came in and they didn't go out again. And in fact, we were seeing some of what turned out to be the most extensive tectonic deformation of the Earth's crust that had ever been recorded in history.
The Alaskan earthquake provided a confirmation of the theory of plate tectonics. A landmass 2/3 the size of California had been deformed, with areas uplifted as much as 38 feet. The pattern of change was completely consistent with the thrusting of the Pacific plate beneath Alaska. Now that the driving force of earthquakes was understood, some researchers believed that prediction was only a matter of time.
One thing that had happened was the 3 countries started major earthquake prediction efforts, the Soviet Union, China, and Japan, about 1965. We were well aware of what they were doing. I think in that period of working on earthquake prediction became something that scientists could work on without having to apologize for. It was a genuine scientific effort.
That effort seemed to pay off in the early 1970s. U.S. scientists were able to confirm a Russian claim that a reliable precursor had been found at last. Prior to an earthquake, seismic waves passing through a fault zone appeared to slow down.
There was great enthusiasm that we understood the process, and we were within 5 to 10 years of predicting earthquakes, and we knew how to do it, and we just needed to get cracking. And it was heady times for the geoscientists.
The prediction effort received a further boost when extraordinary news arrived from China. On February 4th, 1975, a magnitude 7.3 earthquake destroyed 90% of the buildings in the town of Haichang. But not before the State Seismological Bureau predicted the earthquake. Tens of thousands of lives were saved.
The Chinese did successfully predict the Haichang earthquake. Evacuations were ordered a few hours before the earthquake. They had a certain hard time convincing people to really go outside, and I know in several of the towns they showed movies in the town square to get people to come outside, in spite of the fact that it was February in Manchuria and probably something like 20 below zero.
The success at Haichang was the culmination of a people's war on earthquakes that had been declared in the early days of the Cultural Revolution. By 1974, the Chinese had set up 17 major observatories, 250 regional seismic stations, and enlisted an army of amateur earthquake watchers, some 100,000 in number. They looked for virtually every kind of precursor that had ever been observed. They monitored foreshocks, swelling of the ground, changes in electrical conductivity, and geomagnetics. The cadres were particularly impressed by the strange behavior of certain animals before the earthquake. After the prediction at Haichang, the Chinese effort became world famous. The success was widely hailed as a turning point in earthquake prediction. "17 months later, on the morning of July 28, 1976, residents of the city of Tangshan were fast asleep. Suddenly, they were catapulted out of bed, then their homes collapsed upon them. There had been no prediction, no warning. "20 square miles of cityscape were in utter ruin. 500,000 people were dead or dying. How had the Chinese succeeded a year and a half before at Haichang?
I think earthquakes follow a wide variety of patterns, and the Haichang earthquake was one of the earthquakes with a lot of precursors. For some reason, it did a lot of deforming before the actual earthquake happened.
The evacuation was based on foreshocks. The morning of that earthquake, there were a lot of magnitude 5 foreshocks right in the area.
With the tragedy of Tangshan, the earthquake prediction effort began to lose its newfound credibility. By this time, the Russian prediction theory had also been called into question. The claims by U.S. researchers that they had found velocity changes before earthquakes did not stand up to scrutiny.
It just wasn't holding up. And now it's pretty well discredited, and it seems like much of the supposed anomalies may have been problems in the way the data was collected. It's a long-standing problem, I think, in earthquake studies, or earthquake prediction research, is one, people want it too badly. There's such a desire for it that it's easy to overestimate what you get. And there's a lot of societal pressure to overestimate it. There's also, it is just so difficult to get a long enough data set. Earthquakes happen on geologic timescales, and we want to operate on human timescales. And we just don't have enough data. You really need to see it for 100 earthquakes. A lot of what goes on in earthquakes is random, so we need to collect a large data set and a good statistical sample. And it's very hard to apply proper statistical techniques to earthquakes just because the data isn't there.
The most meticulous and focused attempt ever undertaken to collect earthquake data sits today on the San Andreas Fault in Central California. It's an unlikely spot. the tiny town of Parkfield would hardly draw notice except for the fact that it experiences a magnitude 6 earthquake with uncanny regularity, every 22 years on average. This makes Parkfield one of the only locations in the world where instruments can be put in place with any assurance of something to measure. In 1985, the USGS set up shop.
There's nothing very complicated about the basic model we're operating on here. Basically, it's strain accumulation due to the plates moving by each other and sudden release. Short-term prediction, in my opinion, depends just really on one thing, and that is that as the strain accumulates just prior to failure, are there any nonlinear or really distinctive departures from simple strain accumulation? And the way I think of it is just taking a stick. If you just take a stick and bend it, you can feel the strain energy piling up in the stick. And if you listen closely, you can hear the stick start to crack before it breaks. The question is, does the earth crack before it breaks?
To answer that question, the serene segment of the fault is the setting for nearly 500 instruments. Sensors buried deep in the earth monitor the slightest movement or strain. Groundwater levels give a broader picture of deformation. Seismographs are deployed as deep as a mile. Instruments are solar-powered. Data is beamed via satellite to USGS headquarters near San Francisco, then back to the local operation, run out of an old farmhouse.
Want to look around in here? This is just the odd jobs room where they do...
Alan Lynn's interest was piqued by the discovery of low-frequency radio waves before the Loma Prieta earthquake.
I think it actually... Then here there's a nice air-conditioned computer room.
Oh, this is very nice.
He invited Anthony Fraser Smith to set up his antennas here at Parkfield. Any new claim about earthquake prediction requires a caution born of experience.
First you go talk to the guy and you sort of look him in the eye. And then if you still believe him, you go home and say a little prayer that it's all true and that it's all going to hold up and that the experiments will be reproducible. In the case of the radio waves, if those signals turn out to be common before large earthquakes, that's revolutionary.
The investment of time, prestige, and resources at Parkfield has been considerable. If the earthquake had maintained its 22-year average, it would have arrived in 1988. Occasionally, the wait has been longer.
The longest one we know of is 34 to 66, 32 years. We're certainly hoping that that's not going to happen again. That will be a bitter pill to swallow.
While the cycle at Parkfield may vary, earthquakes occur sufficiently often to reveal a pattern. Along other sections of the fault, centuries pass between events. South of Parkfield, a 200-mile segment of the San Andreas has been locked up since the last great earthquake, when it was displaced a full 10 meters, over 30 feet. That was in 1857. An effort to identify patterns of long-term recurrence began in 1975 here on the Carrizo Plain in Central California. A young geologist named Kerry C. started work that would lead to a new approach to earthquake prediction based not on precursors, but on the prehistoric record. The theory of plate tectonics told him that the buildup of strain along the fault was steady. Perhaps there was some regularity in the release. Another 10-meter earthquake might take place when another 10 meters of strain had built up. Kerry needed to figure out the rate at which the strain was accumulating. A stream that had been moved off course by a series of earthquakes offered a tantalizing clue.
We recognize that this channel at one time flowed across the fault in a straight line, but it has been offset now 130 meters, so that it now has a dog leg in it along the fault and then continues to flow out into the valley.
If Carey could determine how long ago the creek ran straight across the fault, then by simply dividing the distance it had moved by the number of years it had taken, he would arrive at the rate of strain accumulation. The history of the now dry stream bed could be read in the way that sediments had been deposited over the centuries. Samples collected at key points would be radiocarbon dated. Their ages established that the river had run straight across the fault 3,700 years ago. Since that time, the fault has moved 130 meters, an average of 3.5 centimeters per year. Based on the rate that strain was building up, it would take 300 years for a similar earthquake to happen again. Carey's forecast for the Carrizo Plain was based on an average interval between earthquakes, but some irregularity was undoubtedly involved. To be more precise, he needed the actual dates of prehistoric earthquakes. He decided to look underground. A trench 12 feet deep has been cut across the fault.
See the gravel? Now which one is it? Oh, okay. I think we may be in business here.
A sedimentary record of the past 3,000 years is exposed.
Really the fault zone.
Supports are put in place to guard against collapse. Each layer is identified and marked. Breaks in the layers are the result of earthquakes. Eventually, samples will be collected and earthquakes dated. Individual earthquakes can be identified with the help of a diagram, like this one made at a site called Pallet Creek.
As the sediments have been accumulating over the past 2 millennia, they've recorded the story of the San Andreas Fault. The reason they've done that is that every 100 or a couple hundred years, the San Andreas Fault breaks and disrupts these sediments, as you can see here. Now, let's look, for example, at this particular place. This layer was the ground surface in 1480 AD, about the time that Columbus was discovering America. So you can imagine a little Native American boy standing here about 4 feet high on this old marshy, boggy ground. If he'd been standing right here, what he would have seen looking out this way is the ground suddenly drop and shift this way during the Great Earthquake. What formed was a scarp about a foot high, or about 30 centimeters high here. You can see this layer has been broken off from its continuation over here. In the succeeding 100 or 200 or 300 years, these layers of sand and silt and peat accumulated and buried that fault scarp completely. So here we have a beautiful example of a buried fault scarp produced by a paleo earthquake, or an ancient prehistoric earthquake, about the time that Columbus was setting foot in North America.
Can I hold it?
Carey C. was one of the pioneers of a new discipline called paleoseismology, now being practiced all over the world. The dates of prehistoric earthquakes that he and others unearthed would be used to project future events. A new approach called earthquake forecasting was underway.
Several of us had started work in the early 1980s on trying to do estimates of probability for the San Andreas Fault and a few other major faults in California, to break the fault up into various segments, and based on the historic or prehistoric earthquakes that we know have occurred there, to try and make a forecast for the next 10 to 30 years of what is the likelihood that various segments will break in a large earthquake.
In 1988, the USGS published a forecast for the San Andreas. Parkfield was given the highest probability in the state, 90% over the next 30 years. The report singled out the Santa Cruz Mountain segment around Loma Prieta. It was assigned the highest risk in Northern California. The most recent forecast gives the San Francisco Bay Area at least a 67% probability of a large earthquake on either the San Andreas or two other faults nearby. Near Los Angeles and San Bernardino, the San Andreas alone is given a minimum 60% risk. Although long-term probabilities may not be satisfying to the average California resident, they are the only kind of warning that gives enough time to regulate development and reinforce structures. As it is often said, earthquakes don't kill people, buildings do. But without questioning the value of long-term forecasts, their scientific validity is still debated.
I don't think the evidence is in. If you go and look at the San Andreas, all the way along it, it's been moving on average 3.5 centimeters a year. But that doesn't mean that on the time scale of 1,000 years, you're going to have exactly your 35 meters. It could be that you're going to have 20 meters in one millennium and 40 meters in another millennium. And we have made the assumption in doing the forecasting that 35 millimeters a year recognized on geologic timescales means 35 millimeters per year being applied somehow to that fault. And that's not necessarily valid. And that's what the big argument is.
Another problem with the forecast is that it doesn't consider as much as half of the seismic activity in Southern California that takes place off of the San Andreas. A 1952 earthquake under the Tehachapi Mountains north of Los Angeles registered a magnitude of 7.7. It is believed to have been caused by a previously unrecognized class of hidden faults that are involved in the formation of the transverse ranges of Southern California. Some experts believe that a hidden thrust fault runs directly under the city of Los Angeles.
Well, if geologic and seismologic evidence really does pull together, there's the possibility that we could have that earthquake under the city of Los Angeles, extending from Whittier through downtown out to Santa Monica. And that would be by far the worst seismic disaster that the country could face.
While the plate boundary along the west coast accounts for most of the seismic energy released in the continental United States, major earthquakes have occurred further east. The buildup of mid-plate strain is very slow, but it can produce earthquakes on cycles approaching thousands rather than hundreds of years. But it is on the West Coast that earthquakes are likely within the lifetime of anyone watching this program. Alan Lind has turned to the seismic record for new insights into the future. He has plotted the earthquake history of the San Francisco Bay Area. 3 faults are involved: the San Andreas, Hayward, and Calaveras. The map reveals that a buildup of activity preceded 1906.
More activity here on the Calaveras, more activity on the Calaveras, and then boom, 1906. Then we go through a very long period after 1906 when you can see that here in the Bay Area proper, there are just no earthquakes greater than magnitude 5. So enough energy is taken out of the ground when you get a really big earthquake that it essentially turns off all the adjacent faults. Then the activity really started in 1979 with a magnitude 6 earthquake on the Calaveras, This sequence from 1979 to 1989 is remarkably similar to the period of activity that preceded 1906. And then, of course, the 1989 Loma Prieta earthquake ruptured this whole zone. It's clear in the Bay Area, all the big earthquakes have occurred in one of these clusters. You have rather clear periods of time with little or no seismicity, then a cluster, and somewhere within the cluster, one or two bigger events will occur. So the question we're really most concerned about is, one, will the Loma Prieta activity continue on up the peninsula? Will we get a magnitude 7 here on the San Andreas that will really be a major threat, a catastrophic threat to San Francisco and Oakland? The other question is the northern part of the Hayward Fault in particular. This is probably the most dangerous segment of a fault in California. We know it's had magnitude 7s in the past. It's certainly capable, it will have them in the future. It runs right through a major urban area, much of which looks like it is particularly vulnerable. Hospitals, schools, freeways, power lines, bridges, freeway interchanges. You want to find those things in the East Bay, you just follow the Hayward Fault. I think the best story about earthquake prediction is really the story of Imamura and Omori from the turn of the century in Japan. Imamura was a young seismologist, really the man, I think, who started the whole field of earthquake prediction, because from 1900 on, he believed he understood the pattern of seismicity along the Japanese islands well enough that he really thought there was going to be a very large earthquake in the Kanto district south of Tokyo within a few decades. And over a period of 20 years, he worked very hard to try to inform the government, the public, wrote papers about it, studied the firefighting situation in Tokyo, warned people in writing that as many as 100,000 people might die in a great fire when this earthquake came. But his efforts were really in vain. There was a much older seismologist at the University of Tokyo, Omori. And Omori believed that Imamura's arguments were irresponsible. And he worked hard to counteract the effect of Imamura's warnings. And because Imamura was so much younger, Omori prevailed. In 1923, Omori, the older gentleman, was in Australia at a scientific meeting, and he was actually in the seismic vault in Sydney looking at the instruments when he saw the pen begin to swing back and forth on the drum. They realized a big earthquake had occurred somewhere in the world. Within a few minutes, he could interpret the record, and he knew that Imamura's earthquake had just happened. Because the earthquake occurred exactly where Imamura felt it would. There was a great fire. 140,000 people died in the earthquake and the fire. And when one looks back at the data they had, one can side either with Imamura or Omori. Neither of them was right. There was inadequate information to make a definitive prediction of any kind. Imamura made the more daring interpretation and turned out to be right in that case. But I think the story perfectly illustrates the dilemma that still faces us today in trying to warn people in the Bay Area about a large upcoming earthquake. We don't know for sure that it's going to happen, and we don't know for sure where it's going to happen. There is no simple answer to the question. All we can try to do, I think, is try to communicate to people what we do understand with all its limitations and uncertainties, and try to help them see that while we can't tell them for sure the earthquake is coming, a big earthquake in the coming decades in the Bay Area is so likely now that I think they should start to behave as if they knew for sure it was going to come. There's some precautions now, I think, that if they're not taken, it will really be reprehensible.
The memory of Loma Prieta lingers. Even though damage was not widespread, it was the nation's most expensive natural disaster, with a price approaching $10 billion in property losses alone. While the loss of life took place principally on one aging freeway, 62 people died. And even though fires were ultimately contained, extinguishing them severely taxed the San Francisco firefighting force. Loma Prieta was not a great earthquake.
Funding for NOVA is provided by the Johnson & Johnson family of companies, supplying health care products worldwide. And Lockheed, a bold new force in systems engineering, management, and technology services for defense, space, and industry. Major funding for NOVA is provided by the financial support of viewers like you. For a transcript of this program, send $5 to this address or call 212-227-READ.
This is PBS.